our previous lecture about alpha, beta, and gamma radiations. Uh, in that particular lectures, we have some discussion about the alpha decay, and we have discussed that alpha particles is basically a helium nucleus consists of two proton and two neutrons. We have mentioned that during alpha decay, uh, the number of protons is being reduced by 2. Similarly, we have discussed that during the alpha decay, the number of neutron is reduced by 2, and the atomic weight as a whole is reduced by 4. So the general equations that represent the alpha decay is given like this. That is, we have a parent nuclei that we denote by capital letter X. We have a substrate Z. That Z basically means the number of proton in that parent nucleus. A is the atomic mass, and N is the number of neutron. So what happened? This parent nuclei, when it's undergo alpha decay, so we have a direct nucleus uh, with a two less number of proton, uh, reductions in the atomic mass by 4, and we have again two less number of the neutron, and with that we have alpha particles. So the practical example is let we have a uranium 238 nucleus, so that when go for alpha decay after a half-life of 4.47 and 10 raised to power 9 years, so we will have a thorium nucleus, a thorium nucleus with the atomic mass 234 and atomic numbers 90. So along with that we have disintegration energy. So what is the disintegration energy? The disintegration energy we denoted by Q, and it is equal to uh, the mass of the parent nucleus that we represent by MP minus the mass of the daughter nucleus, and minus the mass of the alpha particles whole multiplied by C square. So if we consider the uranium 238 nucleus, so in that particular case we have the value of MP that we represent by Mu, U for the uranium nucleus. So we have that 238.050784 U atomic mass unit, mass of the direct nucleus, which in that particular case is thorium nucleus. So the atomic mass of the thorium nucleus is 234.043593 U, minus the alpha particle, the mass of the alpha particle, which is equal to 4.002602 atomic mass unit. So now you just put the values here. We just put the values in these particular equations, so we get the difference that is equal to 0.004589 U. Now we have to multiply this with the C square. The C square has a value 931.502. So we have the value for the Q, which is equal to 4.275, and this as a whole we know that it's called disintegration energy. So now we have a question here. We have some discussion here. Okay, and which is that most of the energy that is we call the disintegration energy as the kinetic energy of the alpha particle. So what actually we have during the when we say that the decay occur, so during the decay uh, the Q value is greater than 0. So what we have, we would say that in that particular reactions if Q value is greater than 0, so we say that and during that particular reaction energy will be reduced. So during spontaneous decay, we can also have spontaneous decay. I mean, we say that all that particular kind of decay which occur all by itself. So during this particular decay, we say here spontaneous decay does not occur if Q value, if disintegration value is smaller than 0. I mean, we have the chances for the spontaneous decay, but here we say that spontaneous decay, it cannot occur if the disintegration energy is smaller than 0. So conservation of energy, conservation of momentum, Uh, that we mean that daughter's nucleus plus alpha particles and energy it gave us this particular value, that is q is equal to kinetic energy of alpha particle plus kinetic energy of the daughter particle. So here from here onward we can calculate the kinetic energy, which is equal to from this particular equations we have this particular equations. So from these equations we can calculate the kinetic energy. Just rearrange these equations. So we have the kinetic energy of the alpha particle is equal to q dot a minus 4 divided by a. Just put the values. If we consider uranium 238 nucleus, so the kinetic energy of the alpha particle which will be released is equal to, after putting all these values, we get that this will be equal to 4.2 mega electron volt. uh, what's beta decay? So here we can say that during beta decay, the nucleus can correct a proton or neutron axis by mutual convergence. We say that inside the nucleus, the conversion take place. The neutron is converting to proton, proton is converting into neutron. So during this conversion, we say that we have beta negative decay and beta positive decay. So what actually we have, either a neutron is converted to proton through beta negative emissions, or proton to neutron through beta positive emissions. Another possibility is during beta decay, uh, we can have capturing. We say that we can have a proton, and that proton can capture an atomic electrons, allowing it to convert into a neutron. We can have a protons, and that proton can capture an atomic electron, after which it can be converted into a neutron. So we have three possibilities for the beta decay. We can either have a neutron which is converting into a proton by the emission of beta negative. We can have a proton. We can have a conversion from proton to neutron through beta positive emissions, and we can have a proton which can capture an electron, and by that we say we can have a convergence from proton to neutrons. So this is some of the mechanism of beta decay. What we have mentioned in the previous slide, that we have a neutron, and that neutron is converting into proton with a beta negative. E negative is basically for the beta negative. Similarly, we can say that we have a proton, and that proton is converting it to a neutron along with that beta positive. Or we say that, as we mentioned in the last slide, we can have an electron captures. That is, uh, during that electron capture, we have a proton. That proton is converting into electron. The E is for an electron, atomic electron. This is an atomic electron. So if you remember, we have a question right in the beginning of the course, that electron or positron is not present at the nucleus prior to decay. So it is created during the decay process. So you can have, or you might be asked a question, if electron or positron cannot reside inside the nucleus, so how they are being produced? Then why it's been emitted from the nucleus? So we already have a lot of discussion about that. So you have to rewind some of your previous concept about this. Here we can consider a practical examples for the beta decay. That is, we have a bismuth atom. So during beta decay, bismuth atom is converted into polonium with the beta negative after a half-life equal to 5 days. And during this particular process, we have a disintegration energy of 1.16 mega electron volt. So if we can plot the kinetic energy of the electron, or kinetic energy of the beta particle, and we plot that against the relativistic number of the electron, so we can have a graph like this. For a range of the energy. We can have further discussion about that in coming slide. So beta decay again, what actually happened during the beta decay? So you know that the masses of the parent and daughter nuclei are both fixed. So we have a question. during the beta decay, the masses of both the parent and daughter nuclides remain the same. So the question is, from where do we have the energy for the beta particle? From energy we mean the kinetic energy for the emission of beta particle. If the masses remain the same, so from where we get the energy for the beta particle? And we also have a problem. We have a problem with the energy conservations and momentum conservation. Energy conservation and momentum conservation, I mean, it's real problem with the beta decay. So it was in 1930 when Pauli suggested that there must be another particle involved. I mean, during the initial process, the initial discussion by beta decay, there was problem about energy conservation and momentum conservation. So it was Pauli in 1930 who said that there must be another particles that involves during the beta decay process. So, I mean, the discussion continues. It's come to Enrico Fermi in 1934, who discovered neutrino. And he, while describing the characteristic of the neutrino, he said that it must be a particle with a charge equal to zero, net charge equal to zero, and mass approximately equal to zero. So this was the real case that momentum conservation's problem. I mean, we have a parent nucleus when it undergoes through beta decay. So we have certain momentum for the daughter nucleus, along with that with the electron or positron. So this was the real problem with the momentum conservations, and this was the problem when it was being resolved. So what we have a particular beta decay process in which we say a proton is converting into a neutron along with a positron. So if you look at the process, uh, during this process, you know that we have three fermions. We have three fermions, that is proton, neutrons, and electrons. In this particular case, it's positron. So these are fermions with the spin equal to 1 by 2. We say that half spin. So you can see from this particular relations, the spin angular momentum is not conserved in the above reactions. Here in this particular reactions, if you look, we have half spin on one side, half spin plus half spin on the other side. Here is a half spin, half integral spin, but here we have on this particular side integral spin. So the spin angular momentum is not conserved. So the other particle, we say that the other particle must have spin equal to 1 by 2. So if you want the momentum to be conserved, we must have particles here, and that particle should have a half integral spin. Just like, for example, we have for the beta negative decay, a beta negative decay occurs. So we say that during this particular process, a neutron, we will have a neutron, and that neutron will be converted into a proton along with the missing particle which was being discovered by Enrico Fermi, and he called that neutrino. So during this particular process, the neutron decay into protons, we will have an electron, and along with the electron we will have a particles that been discovered by Enrico Fermi. We call that antineutrino. Antineutrino will be accompanied by these particular reactions during the conversion of a neutron into proton. That is, we have a decay of the pre-neutrons. We have pre-neutrons with a lifetime equal to approximately 886 seconds. So after that, that neutron is converted into protons with the electron and antineutrino. Similarly, we have beta positive decay, in which we have a proton, and that proton is converted into neutron plus positron along with the neutrino. So we say that in this particular case we have electron neutrino pair. So here we have a questions that I want to put for you, and the question is, here we say that decay of a free neutron. So can we have it for a free neutron? Or let's suppose I say it cannot occur for a free proton. So what will be your answer? I just put that discussion for you people. So the complete process of the beta decay is what we have. The continuous energy distributions and the beta decay could only be explained with the presence of this particle called neutrino. I mean that what I mean to say that without mentioning or without stating something about neutrino, we cannot completely describe the process of the beta decay. So here we have the complete descriptions of the beta decay process. That is, for example, we have iodine. Iodine after beta decay is converting into a xenon along with the beta negative plus anti-neutrino. Beta negative along with that anti-neutrino. Similarly, if we have aluminium and after beta decay, beta positive decay, we have what magnesium nucleus, but the particle here is what is a neutrino. The same is the case for the electron capture, that we have manganese atoms. When it captures the electron, so it's been converted into chromium along with that antineutrino. So it's the whole process for the complete process for the beta decay. So what about the gamma radiations? What is gamma? So radioactive gamma emission is analogous to that of atomic radiations. So you know about the atomic radiations, you have studied that in your bachelor classes. What we have for that? So we said in an excited state decays to a lower state. We say that okay, what we have actually an excited state. Uh, you people have studied that in your previous courses. We have when an atoms get an energy, so it goes to an excited state and it remains in that excited state unless it do not emit that particular amount of the energy which it has observed. So it's emitted energy, so it didn't come back to the excited state. So you're saying this, why we're saying that the gamma decay is something like that particular I mean it's analogous to that particular situations. So half-lives for the gamma emissions are quite short, and generally we say it's less than 10 raised to power minus 9 seconds. So half-life of gamma radiations is very short. But there are also gamma emissions with significantly longer half-lives with hours and days. I mean we have normal, it's the normal duration for the gamma decay. I mean it's a normal duration 10 raised to power minus 9 second, but we can say that it's also a longer durations, and the longer half lives is hour. I mean we can that can last per hours and even for days for the gamma radiations. uh, what actually happened during the gamma decay? So during the gamma decay, we should have an isomer. You know about isomer, a nucleus and an excited state, excited energy state. So from excited energy state, like we have arginatum, I mean saying silver nucleus and excited state. So when it de-excites, so it's simply what it do, it emit the energy in the form of a gamma radiation. So what it mean? It mean that no change either a number of proton, neutron, or atomic mass. What it mean? It mean that the total number of neutron, proton, or atomic masses remain the same. What actually happens? We say that during the gamma decay, nucleus just from the excited state goes to uh, uh, the lower energy state, or simply we say that it's de-excited. But it's not only the way that nucleus is de-excited. Nucleus can also de-excite by internal convergence. What's mean by an internal conversion? We say that during the internal convergence, excess energy given to an atomic electron, just like this. We say that inside its nucleus can also be de-excited by giving the excess energy to an atomic electron. Uh, some other possibilities in the case of spontaneous fissions. I mean, we say nuclear physics 2 course, we will discuss about nuclear fission. Fission is basically the splitting up a heavier nucleus and two or more daughter nuclei. So we say that there are some nuclei that fission spontaneously. I mean, uh, in nuclear physics 2 we will discuss. Normally we do have fissions, that is we bombard a projectile on a target nucleus. So with that the target nucleus is split up into particles and we call that efficient process. But in some cases, we say that some unstable nuclei, after a certain time, after its particular half-life, we say that it can goes to fission by itself. So that we call a spontaneous fission. And these situations, we say that similar to the neutron-induced fissions, they occur in reactors, with the exception that no neutron is necessary to analyze the process of the fission. I mean, the fission that we perform and the nuclear reactions, and the nuclear reactors differ from that of spontaneous fissions. That is, the fissions that we perform in the nuclear reactions need a neutrons to be bombarded on the target nucleus. But in case of spontaneous fissions, we don't need any neutron to bombard on the target nucleus. So in the process, we have a heavy nucleus where the axis of the neutron is split into two lighter nuclei. I mean, we have for the spontaneous fission, we have a heavier unstable nucleus. So that particular nucleus, it undergoes into disintegrations without any bombardment from the outside. So the fission products are not rigidly determined as in the case of alpha and beta decay, but are statistically distributed. Some of the examples we have that we have fermium, and that fermium has a half-life equal to 2.6 hours, after which this particular nucleus goes to spontaneous fission. I mean, it's itself is converted into daughter nuclei. Similarly, we have californium with a half-life equal to 60.5 days, after which it go under spontaneous fission with the enormous amounts of energy. Uh, so next we have to discuss about the quantum theory of radioactive decay. So I think that will be okay if we discuss in the on the next lectures. So next we will discuss about question and